Okay. Hello, everyone. I'm Chris Connor. I'm an assistant professor from Brigham and Women's Hospital in Boston, and I also have a basic science research lab, which is over at Boston University. And Jan asked me if I would talk about machine learning, which is an enormous topic, and therefore if I would also do it quickly. So that is what I'm going to try to do. So the talk is called Machine Learning in a Hurry, or AI Too Long Didn't Read. And the reason for this is because artificial intelligence and machine learning seems to go along in stops and starts. There are great leaps forward, and then nothing seems to happen for many years. And I don't think there's any doubt that right now we are in one of those leaps forward. There's been astonishing progress in many areas that were previously thought to be almost intractable, and yet suddenly we have commercial solutions to a lot of these. So language translation is based on a principle called sequence-to-sequence translation, in which you're essentially mapping the statistical likelihood of a sequence of symbols in one language to a sequence of symbols in another language. Image recognition is based on things called deep neural networks or residual neural networks. Natural speech processing is based on something called hidden Markov modeling. Textual analysis draws on a bunch of those, and then self-learning is this result that came out recently from DeepMind, where they managed to get a computer to train itself to play Go and play chess only from the knowledge of the rules and to reach a superhuman level of performance. And 10 years ago, I don't think there was anyone who thought that was going to be possible in this sort of time frame. So all of a sudden, there's this urge to apply all these technologies to medicine, of course, and to anesthesia. Well, to get into these, you have to get into mathematics, and that creates a learning curve. And really, the effect I would like to achieve is something like this, in which I gently ease you into some machine learning concepts and try to avoid this feeling, which I suspect is rather more common. Now, when I was training to be an engineer, one of my professors told me that if you wanted to convince an audience of something using mathematics, you had to come up with the consequences of the mathematics, then you had to tell the audience a story, and then you had to take the mathematics, put it in your desk drawer, and never show it to anyone. So with that in mind, I'd like to begin with a story. So it turns out I'm probably not going to become incredibly wealthy from anesthesia, so I might become an internationally famous author. So here is the first sentence from my new novel. All right, so here's the sentence, and this is on Google Translate. And in fact, this will still work today, I believe, even though I wrote it a couple of months ago. So the sentence is, his car was his car, and her car was her car. A perfectly simple English language sentence that doesn't use any words that you probably didn't learn in your first month of learning English as a second language. And the sense that you get from this, from reading it as a human being, is that the protagonists in my novel are a successful professional couple who have grown apart over the passage of time. Yes? Does everyone feel that from my sentence? Does that resonate with anyone? Okay, and if I ask Google Translate to translate my novel into French, it does this. Now, you may not read French, but that is nonsense, okay? Because in English, the possessive pronoun binds to the gender of the person doing the possessing. In French, it binds to the gender of the object which is possessed. So in French, la voiture is female, and so it uses sa voiture both times. The closest translation back into English would be their car was their car, and their car was their car. Okay, so Google Translate has failed to understand essentially the whole point of the sentence, that the meaning has been lost. You can actually force it to do it. My French is not great, but I was able to come up with this, which sort of works, but the translation into English is pretty awful and also doesn't really capture the meaning. I will say, since I'm here in Belgium, if you do it in Dutch, it works great. So possibly the limitation was there. And when I say that Google Translate didn't understand the sentence, remember this is done with sequence-to-sequence translation. And what I mean by that is that Google Translate has never once understood any sentence that has been said to it. It's merely matching statistically a sequence of symbols in one grammar to a sequence of symbols in the other grammar. And it does that well enough that most of the time it is just about able to trick you into thinking that it can understand and translate what you've said. But relatively simple things will defeat it. All right, So when does AI work best? Well, there's really two circumstances. So AI works very well presently when you have a closed problem. And what I mean by a closed problem is one where potentially I can enumerate, I can say what all the possible moves are and what all the possible responses are. So the problem is described, is sort of fenced off. There's a limit to what the problem can be. And that's really like board games. I mean, this is where we've seen the greatest progression. So there's chess. Everyone can see the board. Everyone takes it in turn to move. The rules are very clear. There are 400 ways, exactly 400 ways, the first two moves of chess can play out. White has 20 choices, black has 20 choices. The first move, there's only 400 ways that can happen. Go, players take it in turns to put stones on the board. It's usually a 19 by 19 grid. So there's 361 ways to begin, 360 ways to respond. That means there's about 130,000 ways of starting a game of Go. So Go is a much harder problem to solve. And poker, there's been a lot of just recent advances in poker AI. Poker is a little more difficult because the game is partially concealed, so not all the information is available to all the participants. And that makes it much harder to value the state of the game to determine whether you're winning or losing. But by averaging over all the possible things that can be done, it can work. So those work really well. Then you have the more commercial applications, and I've just shown you Google Translate. So these work best now where there's a single well-defined task that you want performed, and you're willing to tolerate it doing it wrong occasionally, or even much of the time. So like on Amazon, when it suggests other things that you might want to buy, if it suggests 8 things and you don't want 7 of them, but you buy 1 of them, then that's more money for Amazon, and that's great. All right? So the threshold for success is really quite low, which, and also this is true, I went on Amazon and this was my suggestion queue. Because my daughter has been buying winter Wellington boots for my daughter, and so Amazon now believes that that is the only thing in the whole world that I care about. So when it says see more, I have to say that you've seen enough. All right, so of these 2 domains, which one is anesthesia? 1 or 2? Who says 1? And no one says 1. Who says 2? Yeah, a few people say 2. It's a trick question. It's none of them. It's not, as I think most of you get, it's not a good fit for either thing that AI is good at the moment. So anesthesia has very high reliability requirements and very pressured requirements to execute those based on multiple sources of information. Also, if I'm trying to take care of a patient in the usual way, I might use all of the knowledge of anesthesia that I've accrued over my training. If I have a patient who's particularly sick, though, I might just try to remember the one patient who was like that, who did well any time in the last 15 years, and just try to make that happen again. So in one instance, I'm using all the knowledge I've acquired as if I were a chess-playing computer. Every chess game is pertinent to what I'm trying to do. And in another circumstance, I'm really rejecting almost all my knowledge and just trying to pick out the one pertinent thing that I know about. And it's not clear that even that modern AI systems have this idea of switching between those modes of thinking. Now, but one thing that AI is really good at, and there have been a couple of papers just recently, last year in anesthesiology, is for us to try to figure out physiological processes that we don't yet understand. So there were papers about using a machine learning algorithm to control remifentanil and propofol infusions, and there was a machine learning algorithm about trying to predict whether patients were going to become hypotensive in the next 15 minutes, which came from Edwards, I think. I'm trying to remember the name of the PI. Is at UCLA, but it just temporarily escapes me.
Martin Cannison.
Thank you, yes. So we have an outcome that we either want to attain or avoid. It's not clear what the data is that would lead us to actually make that decision, but we believe that the information is present in a diffuse form in the data we can get from the patient. How are we going to try to figure out a decision rule to help us perform that work and make that decision? And AI can help us with this. And there are some simple techniques you can use, and then I'm going to go to more complicated ones. So here's the easiest one. So let's say that we want to know whether someone is easy to intubate or difficult to intubate, a yes-no decision. Or did they do well in the ICU, or did they not do well in the ICU? And we've got a couple of parameters that we believe feed into that. If we believe it's the airway, we might use Mallampati and thyromental distance. If we believe it's how well they did in the ICU, we might plot glucose, average glucose and average potassium. Now, in both of those cases, you already have intuition about what the graph would look like, and that's cheating, that's understanding, and the computer can't do that. So I have to bring out an abstract thing that you won't have any intuition about. So now we have A and B, and we have some good outcomes which are in circles, and we have some bad outcomes that are in crosses. How could we do some machine learning to help figure out a decision rule? Well, one of the things we need is something called a discriminant. A discriminant is the deciding line. So ultimately, the computer has to make a decision, so we have to have a way that that decision is made. So let's start off with a really simple one. Let's do a linear one. So I can put a line on like this. So this is just a straight diagonal line. So this is A equals B. It's actually a little more clever if you say it's B minus A equals 0, which I'm sure you agree is the same thing. That gives you the line. But now if B is greater than A, then it's positive and it says it's okay, it's in the top. And if B minus A is negative, then that means it's in the bottom and it's bad. And if you do this, well, it sort of does okay. It gets most of the crosses in the correct area. The green is not so great because it's got crosses in there. So this would have, I think, good sensitivity, but really bad specificity. If this was the airway, you'd be getting burned by a bunch of those X's if it turned out to be more difficult than you had guessed. So this is an underfit model. It doesn't capture the problem. We need a better model. Can we do better? Oh yeah, we can definitely do better. Well, we could do this. All right. Now, this is obviously an extremely overfit model. I have just simply drawn lines in order to make it work. So this is the equivalent of using thousands of variables to fit the problem. And if you do that, you can make it work perfectly, but it will not generalize to your validation data. So you will have made a model that is useless. And this is where you need to have training data and validation data. Actually, the best model for this is this one. This is a quadratic curve. I don't know how many of you would have seen that in the data. It's not actually obvious that that is the best one. I can tell you for certain that this is the best one because I made the data in order to fit that curve. And then I spattered some errors on it in order to make it a little unclearer. So I know this is the correct answer, but real life is rarely so. Consider it. There's another technique that's really useful called principal component analysis. You heard about something called independent component analysis already. PCA is a way to reduce the dimensionality of your data. So maybe your data set is just too complicated and you want to make a simple rule, but you need to throw a lot of the data away. How does that work? Well, there's a statistical way for doing it. I'm going to sort of summarize it. PCA is used by online dating services. This is the easiest way to characterize it. So you do a big personality questionnaire of how much you like various things. It then does the PCA on that to figure out what you like as a set of axes, and then it just searches for the person of the gender or genders that you desire who has a well-matched axis set to you. So here's an example since you went on a walk. You know, do you like long walks on the beach? Do you like long walks in the hills? Do you like long walks in Sweden? Well, you just like walking. So that's all you need to know. And PCA is a way of doing that simplification. And this is actually patented. So you can go look this up in the online patent database. So romance isn't dead, it just got patented. And I don't know how many of you, actually, because there's a lot of younger house officers here, I guess, how many of you met your significant other through a mediated online dating service? Sometimes in longer lectures, I ask people to hum in a deniable way if that was their thing. I will just say that this is the 21st century and that is no longer considered shameful. So, but let's talk about neural networks, because I think that's what you really wanted to know about. So here's a neural network, a very general one. So again, I have two features, S and T, and it doesn't really matter what they are. It could be whether someone has left ventricular hypertrophy, they're S and T segments. It goes through this weighting network where different weights are applied to different connections, and all these things are summed to produce an outcome. And this is called forward propagation. So you take the features and you forward propagate to generate the outcome. The outcome tells you what category you fell into, good or bad. That's how it works going forwards. How does it learn? Well, there's something called backward propagation, where you adjust the weights in order to fix training errors in your training set. So you try to match your training set, you make errors, and then backward propagation changes the weights in order to try to reduce the errors. How does backward propagation work? It works the same way as office politics works. All right? If there is a mistake that is made, the blame falls upon the weights that most contributed to that error, and they get the most adjusted or fired. Now, you might say, Chris, I know something about office politics. isn't there a problem where everyone was to blame, so really nobody was to blame? And the answer is yes. And in machine learning, that is called the loss gradient problem, where there's just no longer anywhere to apply it over. The learning gradient becomes indistinct. You can also say, well, I know something about office politics. Is it possible for one thing to dominate all the others so you get an unsatisfactory solution? Yes, that happens too. Neural networks aren't guaranteed to necessarily converge to the best solution, unlike some of the techniques I've shown you. They're also rather inscrutable, so it can be very hard to say from the weights that you get how it's actually working. One advantage is, though, is that because it only depends on the weight, you can, in principle, fit any model that exists, and it comes with no preconceptions about what the response of the data is going to look like. So here's a way that we could make a machine learning algorithm to try to predict difficulty intubation based on how people look. You will do it if you're a clinical anesthesiologist. You could look at me, and I bet you could hazard a guess as to what my Cormac and Lane view would be. In fact, some of you probably did it without even thinking about it already. We could do a neural network like this, where it takes the color intensity of every pixel and then weights it, and then we train it on a lot of people, and then it eventually spits out a prediction grade. And in principle, this is workable. The way I've structured the neural network here is not optimal. It would have far too many variables, and it would take a long time to train. So a lot of the modern advances in neural networks have been using different constructions. So convolutional neural networks are important for machine imaging, and they essentially do a sequence of reductions in which the same neural network map is applied to adjacent areas of the image, and it reduces the image down in complexity. And this is sort of the same idea. This is inspired biologically by the idea of retinal cells that are edge responsive. So you use the same variables, but just apply it all over the image. So your variable count goes way down. That's one new technique. The other one I mentioned was residual neural networks. What's different here is that you have a neural network layer, but it's also bypassed, and the previous result is added in again. Now, the reason why this is potentially good is because if a network has nothing more to say or nothing more to add, it's easier for the intermediate layer to go to 0. So then it just passes right through. Because if I take something, multiply it by 0 and add what I started with, it's the same. Yeah? Okay. This also makes it easier for gradients to propagate backwards because there's layers that it can skip over. So the learning gradient has a way to move backwards through the network more efficiently by skipping. And this is inspired biologically by pyramidal cortical neurons that you also saw in the Cajal pictures. And also, I will say, in the connectome image that is on the poster. So I wanted to just talk briefly about this neuroconnectome image because my basic science work, to which we also apply artificial intelligence, involves C. elegans. This is a very simple worm, and we image its head, and it is fluorescently labeled so that we can see the activity of each one of its neurons. Here's a close-up of its head. I'm just rotating it mathematically. The red dots are the nuclei of the neurons, and the green flashing is the calcium activity, measured by GCAM, which you also already saw today. And so by doing this, we can actually see the activity of each neuron individually, and then we can try to figure out how they relate to each other in their behavior, and essentially try to discriminate how anesthesia works. And we can do that. Whoops, sorry, this is preliminary data. So you've seen a correlation map already. This is a correlation map from our lab. This is unpublished data. So at 0% correlation, that's how a worm's brain normally behaves. At 4%, you can see the correlation sort of gets smashed to bits. All of a sudden, the same pattern is not there. And at 8%, there's some more correlation again, but now the pattern is different, and proximal neurons have become locked and well correlated to each other. That's hard to interpret because that's 120-dimensional data. I can do PCA, which I just showed you, and reduce it to 3 dimensions. So now it looks like this. So at 0%, the worm has these neuronal states that it orbits between, and there's areas of the map where it doesn't go, but it just moves between those neuronal states. And I've colored it by the activity of one neuron, AVA, which describes whether the worm is moving forwards and backwards. And so you can see that it has movement states that are very well neurological states that are very well correlated to its behavior. As you start to anesthetize it, if you look at 4% isoflurane, now it's a lot more wiggly, and the coloration of the neuron doesn't match nearly so well to the cycling of the state. And if you look at 8%, it actually starts off out here and then just drops down into the middle and sits there and can't get out of that state. So if you had to sum it up in U2 lyrics, The first one is the control. The one in the middle is that she moves in mysterious ways. And the one on the end is that you've got stuck in a moment and you can't get out of it. And those are the different kinds of anesthesia. And this is entirely consistent, as you very helpfully said, with the question that I asked Alex about the increase in neuronal mass and neurons locking to each other. So that was some very nice real-time collaboration. We can also just go a little further, and I think this is my last slide. So this is, oh no, I have two more. This is a worm now, so instead of having red dots for its neurons, it's actually individually colored. So there's a different color for each neuron. This is incredible genetic engineering. So you can disambiguate each one from its neighbors. And so you can now know exactly what each neuron is doing in the worm at any particular time. The one other thing I wanted to talk to you about, so once we've gone over machine learning techniques, is, well, how do you want to do it? And there's this idea of a decision loop, excuse me. This is called the OODA loop, which is an idea of how humans make decisions, which was developed by an Air Force colonel called John Boyd, about how to win in a dogfight. So whoever wins in a plain dogfight is whoever can execute their decision loop the fastest, and so anticipate the other person and shoot them down. It also works well for really any decision-making task. If you do that, you have to decide where you want the human to be, and I'm sure this is going to come up later. You can either have the human in the loop, which is what we have right now for most of our anesthesia systems, where you might have decision support tools, but ultimately everything depends on what decision you make and how you use it. You are absolutely necessary for controlling the system. We are moving a little bit more now gradually in anesthesia to on-the-loop systems. And this is, I think you're ahead of us in Europe with this, but stuff like VRG targeting or TIVA, or target-controlled TIVA, which you've had for more than a long time now, that we do not have in the US, are all really on-the-loop systems in which the system is able to take some control of the process, but you have to sit there and watch it to make sure it's okay. The goal eventually is to go to a completely out-of-the-loop system where the machinery is just capable of taking care of the person themselves. And so that is really the goal that people want to reach in anesthesia and in medicine in general. I'm not sure we're there yet. I'm not even terribly sure we're particularly close. I think we're still just hovering between stages 1 and 2. But those were the concepts that I wanted to give you most of all in a hurry about how machine learning works. So if you have any questions about that, now's a good time.